Hi, my name is Adrian Thinnyun, and I'm working with Dr. Reed Simmons in the Reliable Autonomous Systems Lab on simulating Quori using ROS and Gazebo. Socially interactive robots have the potential for a wide range of applications, including manning storefronts, serving as research technicians, and assisting elderly or handicapped people. In order for robots to perform well in these applications, they must have strong capabilities for social interaction. Two of the most popular socially interactive robots, SoftBank's Pepper and Now, have been used in a wide variety of professional, research, and recreational activities. However, their high costs can make them prohibitively expensive to use for research groups with limited resources. Quori is an affordable alternative for conducting human-robot interaction research. With an expressive projected face, two gesturing arms, and a bowing waist, Quori has the potential to easily generate versatile social behaviors. However, designing and implementing social skills and behaviors for Quori is currently a difficult task due to the limited number of models available and the lack of a proper simulation environment. Having a proper simulation environment would make the development and testing of algorithms for Quori much easier. In addition to developing a simulator for Quori, we also present work on developing nonverbal behaviors appropriate for social interaction. Humans use a wide variety of poses and gestures to convey emotions and other affective information over the course of natural conversation. For example, someone experiencing anxiety or panic may lean backwards, while someone experiencing joy may move their arms up and down. Thus, having the ability to produce these gestures seamlessly and accurately within the context of a conversation is critical to Quori's capability for social interaction. We use the open-source software Gazebo as the environment for our simulator. Gazebo is a popular robot simulator that has already been used to simulate robots frequently used in HRI research, including Pepper and Now. A Unified Robot Description Format, or URDF file, is used to describe the virtual model of Quori, containing information about the various links of the model and their associated masses, inertia matrices, and joints. This information is extracted by the engine and used to render the robot in a 3D environment, as well as to simulate physical forces acting upon it and enforce collision checking. The ROS control framework allows for control of the robot using standard ROS topics, nodes, and messages. A variety of controllers are available, each with its own parameters, message type, and function. We chose to use a joint trajectory controller as the main controller for Quori's joints. This controller accepts joint trajectory messages as input, which contain a list of waypoints specifying the position, velocity, and acceleration of each joint at various time steps. We felt that this controller type gave us the necessary freedom and flexibility to accurately produce the diverse set of movements needed for nonverbal communication. To make the description of arm movements easier, we have also implemented an inverse kinematics solution that converts Cartesian points into the joint angles needed to reach them. For a given arm, we define θ1 as the rotation of the arm's joint and θ2 as its abduction/adduction. As depicted in the diagram on the left, C sub 0 indicates the origin of the arm joint and P sub A denotes an arbitrary point on the arm. Finally, we define the coordinate plane such that the x-axis points out to the front of the robot, the y-axis points out to the side of the robot from which the arm originates, and the z-axis is normal to the ground plane, assuming the torso is vertical. We chose to define the coordinate planes for the left and right arms as reflections of one another so that inputting the same command for both arms would lead to symmetrical movement. Using this framework, we have designed a wide variety of behaviors based on Quori's available degrees of freedom. By adjusting the start positions, end positions, and speed of Quori's torso and arms, we can generate a large range of possible expressions and motions for Quori to perform. For example, one possible motion involves Quori slowly leaning backwards and raising its arms in the air. Another possible motion involves Quori quickly leaning forward and lowering a single arm. Thus, we can use varying speeds, degrees, and symmetries of movement in order to help differentiate the behaviors we produce. In the future, we would like to expand on this work in a few key ways. We intend to conduct a survey to gather consensus about the perceived emotional state of Quori as it makes the various poses and movements we have generated through this work. This information can then be used in order to properly develop nonverbal social behaviors for Quori that it can integrate into its interactions with real people. Additionally, although we have precise control over Quori's upper body motions, our control of Quori's wheels and movement is currently limited. We plan to implement a differential drive controller based on the Jacobian to coordinate the base and turret motors to achieve omnidirectional capability, and eventually develop coordinated motions such as facing a given point in space while moving. Thank you for listening to this presentation on simulating Quori using ROS and Gazebo. Have a wonderful day.